Well, it really gets at the heart of what reality even means.
Yeah.
The question is, can an object's de Broglie wavelength actually be shorter than the Planck length? Now, you might initially think, looking at, say, standard quantum mechanics, well, the math seems okay. Maybe.
Right. On the surface, mathematically, you could plug in numbers.
Yeah, but the energies involved, oh boy, they change everything. We're going to explore this this deep conflict, really, between the quantum idea of momentum as this continuous wave and this fundamental limit, the Planck length. That's the scale where gravity and quantum mechanics just, collide. They become inseparable.
Exactly. And our mission here for this deep dive, it isn't really about finding some even tinier bit of matter. It's more about understanding how our fundamental ideas, our concepts of matter, wave, even length itself, how they start to break down when you push them this hard to this extreme scale. We'll navigate this using a few different theoretical viewpoints. It's pretty mind-bending stuff.
Okay, so here's the plan. First, we really need to get a handle on the immense energy we're talking about here. Just thinking about these scales involves crazy amounts of energy. Then we'll look at how gravity seems to throw up this barrier, like a black hole information wall that stops us seeing beyond the Planck scale. After that, we'll explore some really interesting ideas that actually modify quantum mechanics itself, like the generalized uncertainty principle. It kind of suggests there is a minimum length built in.
A fundamental limit, yeah.
And finally, we'll touch on what the big theories of quantum gravity think. String theory, loop quantum gravity, what they say about reality down there. They basically redefine the whole picture. Okay, let's get into it. All right, first things first. We need to talk about Louis de Broglie. This was back in what, 1924?
1924, yes.
He came up with this absolutely revolutionary idea that all matter, not just light, exhibits wave-like properties, wave-particle duality. It's like the bedrock of quantum mechanics now.
It really is. And it wasn't just a neat idea on paper.
No, definitely not. It got verified experimentally just a few years later, 1927. Davison, Germer, Thomson, they showed electrons diffracting, acting like waves. Incredible.
And it's really important to be clear what this de Broglie wave is. It's not like a wave in water, something physical you can, point to. It's a probability wave. Think of it like where the particle is likely to be found. More wave intensity means higher probability.
Right. So for big things like a car, you mentioned it, the 1,000-kilogram car example.
Yeah. For something like that, the wavelength is ridiculously small, like 10 to the minus 38 meters. Utterly, utterly unobservable. It has no practical effect.
But for tiny things like electrons.
Now that's different. For an electron, its de Broglie wavelength can be similar to the spacing between atoms in a crystal. And that's why we see quantum effects like electron diffraction. It becomes measurable, significant.
Okay, so that's the wave side. Now, the other piece, the Planck length, this thing is just mind-bogglingly small. Like 1.6 times 10 to the minus 35 meters, billions and billions of times smaller than an atom.
It's almost impossible to visualize, yeah.
And what strikes me is how we get this number. It comes from combining three fundamental constants of nature. C, the speed of light, G, the gravitational constant, and the reduced Planck constant. Does pulling it from those three pillars mean it's like a truly fundamental, unavoidable scale in the universe?
It strongly suggests that, yes. But maybe not in the way people often think. It's not like a tiny pixel or a grain that space is made of. That's a common misconception.
Okay, so what is its significance then?
Its real significance is it's the scale where our current best theories of physics are expected to just stop working properly. General relativity, which handles gravity, and the standard model for particles and other forces that can't both be right at the Planck scale. Down there, the quantum effects of gravity itself should become dominant. The smooth fabric of space-time we usually imagine is thought to dissolve into this sort of chaotic probabilistic mess, a quantum foam.
Quantum foam, wow, okay. So our usual ideas of distance, of smoothness, they just lose their meaning. Okay, now, here's where it gets really interesting, connecting these two ideas. What happens if you try to calculate the energy a particle would need to have a de Broglie wavelength as short as the Planck length?
Go on.
The answer is astronomical, colossal. The energy comes out to be around the Planck energy, which is roughly 2 billion joules.
Yeah, about 1.96 times 109 joules.
That's like the energy in a full tank of gasoline. Wasn't that the analogy? All packed into one single particle.
It's an incredible concentration of energy.
And what's really wild is that this energy requirement, it basically doesn't depend on the particle's rest mass, an electron, a proton, whatever. To get that tiny wavelength, the kinetic energy just dominates everything else.
And that calculation is the crucial link because, okay, a tiny de Broglie wavelength means, by definition, a huge momentum. Then special relativity tells us huge momentum means huge energy, E phi c for relativistic particles. And then general relativity tells us that huge energy gravitates just like mass, EMC2, effectively.
So you can't just shrink the wavelength in isolation, pushing quantum mechanics that hard forces this unavoidable showdown with gravity.
Exactly. It's not just a quantum problem anymore. Gravity has to get involved.
So, okay, if we actually manage to pump a particle up with that much energy, it wouldn't just stay as a simple little particle, would it? It must fundamentally change.
It absolutely transforms. And to see why, we need to consider these two sort of competing length scales that characterize any object with mass and energy. I sometimes call it the duality of length scales.
Okay.
On one hand, there's the Compton wavelength. That's a quantum mechanical thing. It basically sets the scale below which you can't really localize a particle without potentially creating new particle-antiparticle pairs. If you try to confine it too tightly, the energy you use starts making new matter.
Right. And for light particles like electrons, the Compton wavelength is relatively large, right?
Yeah. For an electron, it's around 10, 12 meters, much larger than the particle itself in a classical sense.
Okay, so that's the quantum scale. What's the other one?
The other one is the Schwarzschild radius. This is pure general relativity. It's the size of the event horizon if you were to collapse that object's mass energy into a black hole.
The point of no return.
The point of no return. And for big things like the sun, this radius is huge kilometers across.
So these scales seem totally opposite. Compton wavelength is big for small masses. Schwarzschild radius is big for large masses.
Exactly. An electron is dominated by its quantum nature, large Compton wavelength, tiny Schwarzschild radius. The sun is dominated by gravity, huge Schwarzschild radius, negligible Compton wavelength.
So, is there a point where they meet?
Yes. And that's the profound part. There is a unique mass scale where these two lengths become comparable, and that scale is the Planck mass. It's about 22 micrograms, surprisingly heavy for a fundamental particle.
Wait, 22 micrograms? That doesn't sound that small.
Not on everyday scales, no. But for a single elementary particle, it's enormous. And at precisely this Planck mass, something incredible happens. The particle's quantum uncertainty size, its Compton wavelength, becomes roughly equal to its own gravitational event horizon size, its Schwarzschild radius.
Wow.
At that point, the very distinction between thinking of it as a fundamental particle and thinking of it as a tiny black hole just dissolves. It becomes meaningless.
Okay, mind slightly blown. So let's loop back to our original question. A particle with a de Broglie wavelength equal to the Planck length. We said its energy corresponds to an effective mass of about twice the Planck mass.
Roughly, yes. M is about 2 times the Planck mass.
So if you try to confine this particle with twice the Planck mass into a region the size of its de Broglie wavelength, which is the Planck length, then its entire mass energy is now inside a space that's actually smaller than its own Schwarzschild radius, because its Schwarzschild radius would be roughly 4 times the Planck length. And that just means inevitable gravitational collapse, right? It has to form a black hole. An event horizon snaps into existence around it.
Precisely. That event horizon acts like a fundamental barrier, an information wall. You wanted to probe inside the Planck length, but the very act of creating the necessary energy conditions seals off that region behind an event horizon.
So you can't actually see the sub-Planckian de Broglie wave you tried to create.
You can't. Any probe you send in, if it has enough energy to resolve that scale, will just get captured by the black hole. If you give the probe more energy to try harder, you just make the black hole bigger. General relativity slams the door shut.
This sounds a bit like that idea, Kugelblitz, making a black hole from pure energy, like concentrated light.
It's a very similar concept, yes. A Kugelblitz is the theoretical idea of forming a black hole purely from radiation, not matter. It's the closest analogy we have.
But does that actually happen?
Well, even there, recent theoretical work, digging into quantum electrodynamics, QED, suggests there might be a kind of quantum veto. The idea is that if you concentrate energy that intensely, the vacuum of space-time itself becomes unstable. QED predicts it would just start spewing out pairs of particles and antiparticles.
Like the vacuum boiling.
In a manner of speaking, yes. This particle creation would effectively dissipate the energy concentration before it could collapse into a black hole. So it seems nature has ways to prevent this stable sub-Planckian state. You either get the black hole information wall, or you get this shower of new particles preventing the collapse. Neither outcome gives you a simple particle with a sub-Planckian wavelength.
Okay, so that's one major roadblock. Gravity just steps in and creates a black hole or a particle storm. But this suggests maybe we should shift perspective. What if the issue isn't just the result of trying to measure something that small, but the fundamental possibility of the measurement itself?
That's a really important angle, and it takes us to the Heisenberg uncertainty principle. The standard version, x to the power 2, implies something quite significant if you think about it.
What's that?
It implies that if you're willing to accept infinite uncertainty in momentum, you can, in principle, measure position with arbitrary precision.
Oh, right. You can know position perfectly if you give up all knowledge of momentum.
Exactly. But the standard Heisenberg principle completely ignores gravity. And that's a huge omission when we're talking about the energies needed to probe tiny distances. Does gravity itself impose a limit?
It feels like it has to. Let's revisit that thought experiment, the Heisenberg microscope. You shoot a high-energy photon at a particle to see where it is.
Right.
Standard HUP says the high-energy photon gives the particle a big, uncertain kick, messing up its momentum. Large kick. Fine. But now let's add gravity. That high-energy photon, because EMC's sick, carries its own equivalent mass. It exerts a gravitational pull on the particle you're trying to measure.
Precisely. And the more energy the photon has, which you need for better position accuracy, smaller decks from the standard HUP, the stronger its gravitational pull and the more it disturbs the particle's position in an unpredictable way.
So there are two sources of position uncertainty now. One from the quantum kick, which gets smaller as photon energy momentum increases, and one from the gravitational pull, which gets larger as photon energy momentum increases.
You've got it. And when you combine these two effects mathematically, something amazing happens. You find there's a point where the total uncertainty in position reaches a minimum value. Trying to get more precise by using even higher energy actually makes the position less certain because the gravitational effect starts to dominate.
And that minimum uncertainty?
It turns out to be on the order of the Planck length. It suggests a fundamental limit imposed by quantum mechanics and gravity working together. You simply cannot measure a position or resolve a distance smaller than the Planck length.
Wow. So the universe itself has a kind of minimum pixel size enforced by its own laws.
That's the physical intuition, yes. And this intuition is captured mathematically in what's called the generalized uncertainty principle, or GUP.
GUP.
It's basically a modification of the fundamental commutation relation between position and momentum operators in quantum mechanics. Instead of x, ac, you add extra terms that become important only at very high energies or momenta.
So it changes the basic rules.
It tweaks the rules to include this gravity-induced uncertainty. The most common form leads to a modified uncertainty relation like x, x2 times 1 plus some factor times.
And that extra term is the key.
That's the key. It means that as momentum uncertainty gets very large, the position uncertainty doesn't go to 0 like in the standard HUP. Instead, because you're dividing by a large but also multiplying by a term involving, the position uncertainty actually starts to increase again after reaching a minimum.
And that minimum value of xs?
The Planck length, approximately. The GUP framework mathematically guarantees this minimum observable length.
So under GUP, a de Broglie wavelength shorter than the Planck length isn't just hard to achieve, it's conceptually impossible, because you can't even measure a length that small.
Exactly. The standard de Broglie relation length is revealed as a low-energy approximation. It breaks down. The GUP implies that the very notion of a wavelength tied to momentum cannot physically correspond to a spatial extent smaller than LP.
Okay, so GUP provides a strong theoretical argument against sub-Planckian wavelengths.
Right.
But it's still a model, right? Not a full theory of everything.
That's right. It's a phenomenological model capturing the expected effects of quantum gravity on measurement. For a complete picture, we need a full theory of quantum gravity. And the two main contenders right now are string theory and loop quantum gravity.
Let's start with string theory. What does it say?
Well, the absolute core idea of string theory is that the fundamental constituents of reality aren't point-like particles anymore. They're tiny, vibrating, one-dimensional filaments called strings.
And these strings are small, like Planck scale small.
The characteristic length scale of these strings, the string length, ULS, is generally assumed to be around the Planck length, yes, maybe slightly larger, but in that ballpark. And the different ways these strings can vibrate correspond to the different fundamental particles we see: electrons, quarks, photons. Crucially, One vibration mode corresponds to the graviton, the hypothetical quantum carrier of the gravitational force. That's why it's a candidate for quantum gravity.
Okay, so if everything is fundamentally a string of about Planck size, what does that imply for probing distances smaller than that? Or having a wavelength smaller than that?
This is where string theory gets really counterintuitive and fascinating. It predicts a phenomenon called T-duality.
T-duality. Sounds complex.
It is, but the basic idea is mind-bending. Imagine one of the extra spatial dimensions required by string theory is curled up into a tiny circle of radius r. T-duality states that the physics described by the theory in this space is exactly identical to the physics in a space where that dimension is curled up with a radius of ls or r, where ls is the fundamental string length.
Wait, so physics at a small radius r is the same as physics at a large radius ls far r?
Identical. Indistinguishable. So if you try to probe smaller and smaller distances, letting r approach 0, the physics becomes exactly the same as probing larger and larger distances where LSR approaches infinity.
My head hurts. So you can't actually probe below the string scale.
You effectively can't. The classical notion of distance fundamentally breaks down. Trying to get smaller than the string scale just wraps you around, in a sense, to a description involving large distances. Smallness beyond this scale becomes an illusion.
So a sub-Planckian de Broglie wavelength.
Has no operational meaning in string theory. The very concept of a continuous wave propagating through a space smaller than the fundamental string length is inconsistent with how string theory describes space-time and distance itself due to T-duality.
Okay. What about the other main theory, loop quantum gravity, LQG? Does it reach a similar conclusion?
It reaches a similar conclusion, but via a very different route. LQG doesn't introduce strings or extra dimensions. Instead, it attempts to directly quantize Einstein's theory of general relativity. It quantizes space-time geometry itself.
Quantizing space-time, what does that mean?
It means treating the fabric of space-time not as a smooth, continuous background stage, but as a dynamic quantum entity built from discrete units. It's background independent.
So space itself is made of chunks.
In a way, yes. LQG predicts that at the Planck scale, the continuum breaks down. Space is fundamentally granular. It's described by structures called spin networks. Think of them as networks of connections, where the links represent fundamental quanta of area and the nodes represent fundamental quanta of volume.
So area and volume themselves come in minimum packet sizes, like energy quanta.
Exactly. There's a smallest possible non-zero area on the order of the Planck area, LPL, and a smallest possible non-zero volume related to the Planck volume. You can't have an area or volume smaller than these minimum chunks.
Ah, okay. So for our question about a wavelength smaller than the Planck length,
LQG gives a very direct answer. There simply is no continuous space below the Planck scale for such a wave to exist or propagate in. The stage itself is discrete. The idea of a smooth wave with a wavelength smaller than the fundamental pixels or atoms of space is simply nonsensical within the theory.
so whether it's gravity creating black holes, or the GUP setting a measurement limit, or string theory's T-duality or LQG's discrete spacetime, they all seem to point in the same direction.
Remarkably consistent, isn't it? Across vastly different theoretical approaches, the conclusion is the same. A physically meaningful de Broglie wavelength shorter than the Planck length appears to be impossible.
So the original premise, just naively extending goal, was flawed from the start.
It seems so. The de Broglie relation is an incredibly successful part of quantum mechanics, but it's ultimately a low-energy, non-gravitational effective theory. The paradox arises purely from extrapolating it into a regime, the Planck scale, where its underlying assumptions, particularly the neglect of gravity and the assumption of continuous spacetime, break down completely.
And the real flaw in the inference, the idea that a sub-Planckian wavelength must mean something exists smaller than the Planck length, is that it treats the particle, its wavelength, and spacetime as separate things.
Precisely. That separation works brilliantly at normal energies, but fails spectacularly at the Planck scale. As we've seen, the immense energy needed for a Planck scale wavelength creates Planck scale effective mass. This mass triggers dominant gravitational effects, black hole formation, or perhaps vacuum instability. And quantum gravity theories tell us that space-time itself becomes a dynamic, quantized entity, inseparable from the matter and energy within it. The object and the space it occupies merge into one quantum gravitational system.
So the thought experiment doesn't reveal a tinier particle, it reveals a new kind of entity. a unified Planck scale object.
That's a great way to put it. It points towards this unification point, and this is beautifully summarized by something called the Compton-Schwarzschild correspondence.
Okay, explain that.
It basically maps out the transition. If an object's mass is much less than the Planck mass, mmp, its quantum nature dominates. Its relevant size is its Compton wavelength, it's a particle. If its mass is much greater than the Planck mass, mmp, its gravitational nature dominates. Its relevant size is its Schwarzschild radius. It's effectively a black hole.
And right at the Planck mass.
Right around the Planck mass, the two descriptions merge. The Compton wavelength and the Schwarzschild radius become roughly equal. The object is its own minimal black hole. Its quantum uncertainty is its event horizon. It's neither purely particle nor purely black hole in the classical sense, but something encompassing both.
So the de Broglie relation, when pushed to this extreme, doesn't break reality. It just points to the boundary of its own usefulness.
Exactly. It acts like a signpost. It tells us, here is where the concepts, particle, wave, continuous space, separate gravity stop making sense. Beyond this point lies a new, unified quantum-gravitational reality.
Wow. Okay. That's quite a journey we just took. From a seemingly simple question about wavelengths to the fundamental structure of space-time and the merging of particles and black holes, it really shows how these deep dives can transform our perspective.
It absolutely does. And it leaves you, the listener, with perhaps a final thought to chew on. If, at the most fundamental scale we can conceive, the distinction between a particle and the space it exists in completely dissolves, what does that really tell us about reality? Is empty space ever truly empty? Or is it this seething, dynamic quantum tapestry from which everything else emerges?
A lot to think about there. Thank you for joining us on this deep dive, and thank you for sending in such a stimulating question and sources. Keep exploring, keep questioning.